Okay, so it's a great pleasure to be here, and thank you very much for the organizers for inviting me here, and it's really a fantastic venue for discussion. So it's really great. So let me check that this is... I was planning on talking on two things. I've added a third thing after some indirect and direct probes from something that Iacopo said in his talk, and from Ashton Bradley putting me on the spot as well. So what I'll be talking about is, well, I hope to be talking about three things. I'm going to start discussing about a single quantum vortex effectively in a 2D trap. And I'd like to discuss about the specific properties of a vortex in a harmonic trap rather than other confinement, and the special role of sound, and what temperature does to destabilize that system. And then I want to move on to discuss the question of what happens when you have many such defects. So these are defects that will be generated through crossing, through quenches, so through crossing the phase transition. And I'd like to discuss basically how they emerge and how they relax. And then I want to move to something which might appear rather unrelated, which is basically what can we understand about dark matter. So what's common about these systems? Well, the first thing that's common about these systems, as I will explain in the last case later on, is the underlying equation. Okay, this is the very well studied Gross-Pitevsky equation, along with some appropriate extensions, obviously, to model each of the systems that's relevant, but it's the basis for all of them. And the other thing that's relevant is the appearance of vortices, again, as I will explain. So let me start with this quasi-two-dimensional vortex problem. So we know that if we have a single vortex in a harmonic trap, it's an infinite trap, so the vortex will go around following the constant radius, the equipotential line. And as you can see from the bottom line, which shows the renormalized density, as it's moving around, it's actually emitting or trying to emit some sound waves. So you have some positive and negative density modulations. Everything is within the trap, so it remains there. But you can see how these are dynamically changing in time. But if you would track this for a very long time, you would see no net decay. Okay, so then the idea is, well, can we, since there is some sound that wants to be emitted, can we actually do something to make sure that the property of this vortex changes? And what we're going to do is, instead of having the system in a single trap, we're going to introduce a cutoff. Okay, a cutoff at around the chemical potential here, such that the sound can escape, but the vortex remains trapped. So I will show you what happens very quickly in a movie. The trap is in the center of the box, okay? So what you will see, I'll play it again. You see very quickly this spiraling out of the vortex. The vortex is emitting all this radiation. I'll play it again so you can see it. It's emitting this radiation, and quickly it becomes unstable because this radiation or sound is able to escape outside the system. Okay? So what we've done is we've allowed a way for this sound that it wants to emit, because it's accelerating in the trap, to actually go out. And what we have is a dipolar radiation pattern along with this vortex motion that gives us this pattern here. So one way to study the stability of the vortex is to think about the energy. Now I'm going to be talking about energy in a region around the vortex core, okay, what we might call the local vortex energy. In a harmonic trap, we saw this density modulation, so the energy will be periodically modulated, but of course it stays constant. There's nowhere for things to go if it's zero temperature. In this double trap, what happens, the energy is going down as the energy is emitted in terms of these sound waves. So that's what's causing the decay, and that's how we can understand it, until basically the vortex reaches the edge, and that's where things change. So we can quantify the rate of energy emission of the system, and actually the rate of energy emission is proportional to the acceleration squared that the vortex is exhibiting in this trap. Okay, and of course this is changing as the trajectory is changing, and it's inversely proportional as well to the frequency. Okay, so this is a general formula. It applies to a whole range of different systems, and similar formulae have also been discussed for in a homogeneous system in classical hydrodynamics, or by mapping vortices to charges, basically. So this is sort of an established general relation, let's say, that we've looked at here.
So then we thought, okay, this cutoff trap was just to understand what is the dynamical mechanism, but we wanted to embed, to see if how one could study that. And so the idea was to put one trap inside another trap, such that the sound can escape to the outer trap. Eventually it will come back, of course, but it has already destabilized the vortex. And that works if you have in a harmonic trap. It works even more if you have a Gaussian trap, because the Gaussian destabilizes even more the vortex, in fact. Okay, so we've done that. We've done a significant amount of study. We would first probe all these things for dark solitons and then see what is the role for a vortex. So in a dark soliton, in a double harmonic trap, you see if I change here the cutoff, so this height of the potential, if it's very high, effectively I get the stable soliton oscillations. If it's not so high, then actually I allow sound to come out, and then the soliton will decay, will get shallower, will travel further out, and that's why its amplitude is increasing. Interestingly, you don't have to have this double cutoff geometry. You can actually have a single trap. So within a Gaussian trap, if it probes not just the bottom of the very harmonic region, but it actually probes broader, the soliton will still decay even though the system is completely confined. So that clearly shows this is a specific property of the harmonic trap. Okay, and then we thought, well, can we do something with that to use that sound for a different purpose? And the idea was to have a double trap configuration and actually put a vortex in each of these traps and see, can we induce vortex crosstalk from one to the other through the sound? And that's what we've done. And for example, here's an example for same vortex polarity. You can see the vortex trajectories are periodically changed due to this sound going from one side to the other. And that is actually, we replaced one vortex by a barrier moving with exactly the same way as the vortex, and it doesn't work. Okay, so it is specific about a vortex-vortex crosstalk. And we can even parametrically drive energy into the vortex state. Okay, and Iacopo mentioned about that. I forget if Michiel also. We didn't do that specifically for the vortex. We did that for the dark soliton. And what we've done here, you can see, we periodically modulated at the very edges of the trap, and actually we could completely stabilize the soliton, make a black soliton in the center just by parametrically driving at a frequency. And we can even think about this example of this double geometry, and we can actually really induce a lot of change in the soliton oscillations across the two wells. So that's all for zero temperature, and we attribute that to the special role of soliton sound or vortex sound interactions, and this is specific to a harmonic trap. We actually tended to call this quasi-integrability of the harmonic trap, in a sense that, well, for these defects at least, but this is kind of a working word rather than a formal mathematical title. So then what happens if you have a thermal cloud? Well, the idea is now, instead of just having your condensate, you have your condensate moving within the incoherent part, the non-condensate. So we have to have two coupled equations. So the condensate is exhibiting the mean field of the non-condensate here, but there's also a term transferring particles between the two systems. And then we need to have an equation for the thermal part of the spectrum, also connected to the Gross-Pitevsky equation. So we have a quantum Boltzmann equation for the thermal cloud. And then what happens is the vortex will actually spiral out due to basically friction with the thermal cloud. So what we see if we have this double system is actually the thermal cloud density, which resides where there is no condensate due to this mean field repulsion, will actually infill the vortex core. It will give it an effective mass, basically. Its quasi-particles are sitting actually inside the vortex, and this is going round as the vortex is moving out. We have the vortex core always infilled by the thermal cloud. So as we increase temperature, of course, there's more and more effect, and it increases rather rapidly. So it is temperature that's destabilizing the effect. What's constant in all of these, to keep same frequencies and everything, the condensate number is constant. We just increase the number of thermal particles, basically due to temperature. Okay, and what we can study now is this damping rate, basically how quickly it's growing radially, and we can see it's highly nonlinear in terms of this reduced temperature over the critical temperature. Now, we haven't directly compared to an experiment. Actually, this can give constrain the values of the friction coefficients.
We haven't done a comparison. Ashton Bradley in his talk did a comparison with his stochastic equation and basically said it's exactly the same with a new equation. About 8 years ago, we published with Ashton using the different form of his stochastic equation, and we had again found a perfect agreement, but it was with a slightly different stochastic equation, so I'm not sure how the two are compatible with his newer results. But basically, Yong-Il Shin's group also did a rather indirect comparison. All this is probing is how this alpha coefficient, mutual friction, is increasing sort of non-linearly, if you like, with temperature, because it's not exactly the same system, so this should not be taken as a good quantitative comparison between the two. Okay, so I'm done with this first vortex part, a single vortex. So now I want to discuss about vortices emerging and relaxing following actually a quench in the parameters. Okay, so this is obviously, the question I want to address is, well, how does coherence grow through defect generation? And this is a very well-known problem in sort of condensed matter and statistical physics, okay, and has a very long history studied in many different systems. So my cartoon picture here, of course, this is characterized by universal critical exponents, so the static critical exponent mu and the dynamical exponent z. And my kind of cartoon of this phase transition crossing is basically you start with something incoherent, you clearly want to end with something coherent. So the idea is you will cross through this critical point, or rather critical region. If you're doing dynamically, there will be some time delay for the system to react. Then you're in a non-equilibrium state. It will gradually relax through phase ordering and get to your final state for the parameters. So in here we have a number of sort of universality sort of class, well, not universality classes. We have a number of universal phenomena happening, and I'm going to be discussing those briefly. Firstly, if you quench at a finite duration, you can discuss Kibble-Zurek growth. Okay, then in the long time, the relaxation happens through phase ordering. Basically, you lose out all these vortices. And through this process of creating a non-equilibrium initial state, you actually get close to these non-thermal fixed points, and then you have universal scaling as you in this neighborhood, if you like, of the non-thermal fixed point. And we also heard this in an earlier talk. So what is Kibble-Zurek mechanism? Well, it tells you if you're quenching at a finite duration, basically, so you're quenching at a rate away from the phase transition, tau q, this is your quench rate in time, then basically you know that as you're approaching the critical point, effectively your relaxation time will be diverging. So as the relaxation time is diverging, as you're moving to cross the phase transition, at some point you're crossing the phase transition faster than the system can actually relax. And that's when you get all these interesting effects coming up. You can define an instantaneous time scale, and basically it's the crossing of this diverging relaxation time and this instantaneous time scale that actually tells you where this system falls out of equilibrium, if you like. Okay, so this occurs at this intersection point there between those two lines. So the whole system cannot follow the external drive. This could be a cooling ramp, or it could be an external pump, for example, depending on your system. So what you get is basically local coherence emerging in regions, and the size of these regions obviously depends on how you're quenching and the details of the parameters. Oops, sorry. Okay, so the average size of the domains in this broken symmetry phase is actually determined by whatever the equilibrium correlation length is at that time. So for these parameters, what's the correlation length basically of the system, and that's what tells you how big the domains will be. So the Kibble-Zurek hypothesis says basically, well, everything can be scaled in terms of this t hat and the length scale at t hat, basically. Okay, and you have a universal evolution function basically coming from the correlations, and it occurs at these characteristic times. So all of these are different ways of testing, if you like, Kibble-Zurek. And another way that was used a lot in the early experiments was you look at the number of defects which will scale with an exponent related to your geometry, dimensionality, and the critical exponents. Okay, so there's been a whole zoo of experiments. I'm just going to briefly say something about an experiment we modeled at Trento, which was in the context of an elongated 3D condensate. Okay, how do we do the modeling? Well, the idea is we model it with this so-called stochastic Gross-Pitevsky equation. It's like a dissipative Gross-Pitevsky equation, but with the noise. So you have to run many, many copies, and then the dissipation, the noise, the strength of the noise is correlated to the dissipation. We have external control parameters to match to the experiment from the initial to the final condition. So we change the temperature and the chemical potential. And I'm going to try and play this movie. It's often temperamental when it's connected to projection. So it seems it's playing. So what you will see is initially it's thermal, and then you see all these vortices emerging, and gradually these vortices are dying themselves out while the system is growing more and more. But as the system is growing, it comes to a point where you really have vortices moving in the system rather than anything else. So here's the whole evolution picture. So we cross the phase transition, we get this emergence of all these vortices. They're very, very turbulent, these vortices, and you get this relaxation. Now the key point of that is actually Kibble-Zurek physics applies here. It's very hard, even numerically, to extract things there. It's not just experimentally. So you can't really do a vortex count at this point. This is effectively a quasi-condensate. There isn't a single mode that is largely occupied. Eventually, one mode will win. So what we can look at is this universal scaling. So we can look at the zero momentum mode occupation, and we can look at the coherence length extracted from the correlation function. And what we see is for different quench rates, you see that the zero momentum occupation, the coherence length exhibit very different dynamics, but the idea is within this critical region, within T hat, all of them, if you do the appropriate scalings, should fall into a single universal curve, and that's what we have actually demonstrated, the emergence of a single. So this is basically verifying Kibble-Zurek by this scaling. Now then the question is, well, what happens at late times? In most early experiments, people were actually counting the vortices, but you can't count vortices there. It was done at a very, very late stage. Actually, this thing here is really very different to what you have at Kibble-Zurek. Interestingly, it seems that the scalings actually remain. The number of vortices changes, but the scaling does not change very much in time. So at late times, if we look, this is, for example, what we see from these simulations that the system, the vortices are dying out. I don't have time to discuss all the details, but the point is in the experiment, they saw they saw vortices, one or more vortices in the system, as you can see here, and we get basically same features emerging at this late time of 200 milliseconds after crossing the phase transition. And we've done other studies as well to compare the experiment. But this is very sort of anisotropic. So the idea is, how do we characterize this second stage where we proceed from Kibble-Zurek to phase relaxation to ordering, and then we need to go to 2D and homogeneous so that it's easier to study that. So in 2D, this is the cartoon picture basically of how you go from disorder to order through the quench. And basically everything depends on this characteristic size, which is growing in time as the system relaxes. Okay, so if this length scale, once this length scale becomes larger than all microscopic length scales, that's when you have this universal scaling, and you have basically the correlation function scales with the universal function in terms of this ratio where LC of t is growing in time. So here I'll show you a movie. We've seen better quality movies here. This is an early movie we did. It just shows you this vortices moving around and dying away, and then you have all you have the phase on the right. Okay, so we looked at that, and we can see we can collapse the correlation functions in an appropriate window, and we can characterize both the decaying number of vortices and the growing length scale, and in the appropriate regime we can find the dynamical critical exponent Z, which is of order 2, which is what is expected, but one would expect as well logarithmic corrections. At least this is sort of the prediction of the 2D XY model, and we didn't really see evidence of these logarithmic corrections. So then we thought, well, what's the question of conservative versus dissipative system? So a closed system versus a system that is coupled.
And we wanted to see the limits. And in both cases, whether it's purely conservative or purely dissipative, we get this scaling emerging. What changes is the value of this critical exponent as you're moving from one regime to the other, and where the logs are important. Okay, so we look at this, firstly, the conservative limit, and what we find is the dynamical critical exponent as you're going, this is gamma, the rate of external coupling, if you like. If it's 0, we find a value which is distinctly clear and lower than 2. Okay, this is without log corrections, of course. We find something which is of the order of 1.7. And when we go to the purely dissipative model, we have to recover 2, and indeed we recover 2 as we expect, but also with log corrections. So the bottom curve is showing everything fit with log corrections and the top without. And so in this limit, we should not include log corrections. In this, we should. What is not clear is how we go from one point to the other, so which curve is relevant and how you transition. And another interesting question is, well, the critical exponent is basically sensitive to whether the system is conservative or open. In addition to the log corrections, the value actually changes. And the question is, how does that relate to experiments? Well, where would an experiment lie? I can't actually tell you that. And we've seen the talk by Maciek earlier about the experiments done in Cambridge. The whole point is, no system is truly conservative. Okay? So I don't know where the experiment would lie. This is an interesting thing to actually discuss. But basically the idea is, as soon as you have some external coupling and dissipation, you jump up from this lower value than 2 towards 2. So this could be a possible explanation. So historically, we actually did a lot of this work first for extern polaritons, but it seemed illogical to introduce in that order here. So this was work done actually by Paolo Comaron, who many of you know when he was my PhD student in Newcastle, jointly with Marcena and her group and Iacopo. And what we did, I don't have time to talk into detail, but we verified both Kibble-Zurek dynamics in this 2D and also the phase ordering with the critical exponent of 2 with logarithmic corrections in this context. Okay, so that's all I wanted to say for this thing, and I want to move to the last part about cosmology. And you might think, well, how does that relate to anything I've discussed? Okay, so let me try and give you a crash course. I'm not a cosmologist, obviously, a crash course into sort of why this is relevant and how it comes out. So we all know, we kind of understand large-scale structure, right? Cold dark matter, or lambda CDM, has been around for a very long time, and it tells us more or less everything we need to know. Well, not quite everything we need to know. So what do we know? We actually have the distribution of light in the universe, and we have to infer that there is some extra matter there. So the way we model that is by saying that there's a corresponding dark matter distribution. Okay, and the idea is then, what is this dark matter and how does it actually relate to things? Now, even though on the large scale, this fantastically models everything, actually recent astrophysical observations tell us that on shorter scales, now what is a short scale? A short scale here is a galaxy. Okay, that's what I mean by short scale. Okay, we have to normalize to the system we're studying. Then basically, there's problems there. Okay, now there might be ways to fix that within lambda CDM by coupling to baryonic matter, invoking second components, and there's various different classes of models that are around trying to deal with that. But one idea that has been around on and off for about 20 years, but has really been picking a lot of attention in the last 7-8 years or so, is this thing called fuzzy dark matter. So what's this fuzzy dark matter? Well, basically it says that dark matter is a coherent galactic-sized superfluid where the collapse due to gravity is actually stabilized by the quantum pressure. So the idea of invoking a superfluid is you have quantum pressure, and quantum pressure stabilizes against gravitational collapse. Okay, so what's the idea? Well, we all know that the Broglie wavelength is inversely proportional to the momentum. So if you want to have a galactic scale condensate, okay, kiloparsec, that's a typical galactic scale, let's say, then you have to have a mass which is insanely low, okay? 10 to the minus 22 eV. This is like insanely low. Just to give you into context, if you've heard about people searching for the QCD axion, this is 10 to the minus 6 MeV.
Okay, so this is 18 orders of magnitude lower. So this, I'm not even going to compare to exciton polaritons, which usually say we have a very low mass, or let alone to rubidium atoms, the standard norm. Okay, so basically the way you model that then to have this quantum pressure is you have a Schrödinger equation, and this is coupled. You have to have gravity there, so it's coupled to the gravitational field which obeys this Poisson equation. And the idea is then, you have, obviously, we're very familiar with these fluid equations. Here's the quantum pressure term emerging, and this stabilizes the density distribution against gravitational collapse. Now, you can actually add, and people do add, self-interactions. So you basically have a Gross-Pitaevsky-Poisson system that you're actually solving. And we've heard about sort of models of solving the Gross-Pitaevsky equation coupled to gravity at the beginning of this lecture by Rahul. Not in the fuzzy dark matter context directly, but it's exactly the same equations, and you change the length scales, you change the masses. Okay, so what's the idea? Well, the cold dark matter model, basically, I told you it has problems at short scales. At large scales, we know we expect this profile here. This is called NFW after Navarro, Frank, and White. Okay, and this is meant to be valid far away from the core of a galaxy. But if you extrapolate back to the core of a galaxy, actually it predicts a divergence, and it has too much matter. And measurements of rotational curves have shown that this is inconsistent with current astrophysical observations, at least in the standard lambda CDM model, without invoking extra degrees of freedom. So the idea is, when you actually add this, when you move to the other picture of fuzzy dark matter, or sometimes called psi dark matter, okay, this solves the problem because quantum pressure stabilizes, and you get what they call a soliton in these systems. Okay, so just to give you an idea, on large scales, they have effectively exactly the same predictions. This is standard cold dark matter model. This is actually fuzzy dark matter model. These were the simulations that re-inspired this field, basically. And the idea is, as you can see, it's effectively the same. They start from the same initial conditions. So on large scales, you can trust as well this fuzzy dark matter. So this might not come as a great surprise when you start thinking about it. Actually, effectively, cold dark matter is n-body simulations, Boltzmann equation. Fuzzy dark matter is Gross-Pitaevsky equation. We all know that Boltzmann equation and Gross-Pitaevsky equation have a lot of similarities, and you can go from one to the other within certain approximations for a lot of the relevant quantities. Okay, so what we've done is we've taken one of these, not this particular one, just a single soliton, and we've tried to analyze the coherence properties of a single soliton. Okay, so what we have, as I said, we have a core, and then on the outside, we expect this NFW profile. And this is sort of a typical profile. Exactly how much you have in the core and how much outside depends on the particular galaxy you're actually studying. So what we wanted to do is understand, well, what does it mean that it's a superfluid or a condensate? So the idea is we could look at the phase space density, for example. So in dimensionless units, we actually see the phase space density changing behavior. You can see this is a log scale, so these are huge orders of magnitude, okay? So it really changes behavior at the point where we jump from this solitonic core to the outside. Now, all of this here is modeled with this is just a Schrödinger equation coupled to a Poisson equation, okay? There is no Boltzmann equation or anything in these simulations to generate these things here, okay? So then we thought, well, we love our condensate, okay? In cold atoms, we think when you have simulations of a noisy field, you look at the largest eigenvalue, which is what we call the Penrose-Sager mode. Let's try and extract the Penrose-Sager mode for this. Well, this green curve is the Penrose-Sager mode of this configuration here. So you can see this is actually your condensate density out of the total density. Of course, we know it should have coherence. So let's think about coherence. Well, what's shown here is the green is the first order sort of off-diagonal correlation function, which measures phase correlations, and the relevant axis here is on the right. You see it basically remains fixed at 1 within the region of the core, and then it very quickly drops to 0, as you would expect, condensed, sort of fluctuating. We can also look at G2, or rather what we're looking at here is not G2, but 2 minus G2.
And what we find is indeed G2 is also 1 inside here, and basically it transitions to the chaotic outside there. So this system, predicted by these equations, actually is perfectly coherent inside and effectively transitions to perfectly incoherent outside. Okay? So what we have shown here in the context of this model always is the galaxy size profile is a purely coherent high density core, okay, which we might want to call a Bose-Einstein condensate, and this is surrounded by an incoherent lower density halo. You see, this is a much lower density because this is on a log scale. Okay? Now, what happens if we look outside? These things are all averaged, radially averaged, and typically we do some time averaging. What happens if you look without the radial averaging and you look at shorter times? And actually what you see is here is the galactic core, and here is actually what you see outside. You actually see lower and higher density regions. They each have their own phase, but they have different phases between them. So between them, you actually have quantum vortices appearing. And so what we find is the surrounding region, this thing described by the NFW, that people describe by particles, you can actually look at it as having quantum vortices there. And here's the kind of movie, that's the galactic core. Now it's real scale, it looks so different because before it was log scale, that's real scale. There's no vortices in the core or the central region, but everything around is a vortex. You can see the phase is changing across the vortices and so on. So this is exactly what the simulations with this model give us. So we can look, for example, at things that we usually look at, the incompressible kinetic energy spectrum, and we will see this k to the -3 scaling law at large K. We can also ask other questions. Well, what about inside the solitonic core? Well, we know the quantum pressure dominates the kinetic energy. It's what actually stabilizes the system against gravity. We can also see that inside, the compressible energy is larger than the incompressible, and this reverses as soon as you go outside the core. So we really see these as two different regions. And so if we go back to the usual way of thinking of a cold, harmonically trapped atomic gas, okay? These are three different, completely random images between them, but they do the trick. We expect to have a condensate in the middle surrounded by a thermal cloud, right? That's what we expect in cold atoms in a harmonic trap. Well, what we have in this fuzzy dark matter model is exactly the same. The scales are different. This is a log scale, but what you have is this Penrose-Sager condensate mode surrounded by this NFW thing. So we can have a bimodal profile that is actually condensate and outside is the non-condensate part. So this is really exactly the same thing. What effectively is happening is gravity is providing the analog of the effective trap for the system. So then we can think, well, what kind of models do we use when we have these two different parts of the system for cold atoms or for liquid helium? Well, we have sort of condensate inside and particles outside. It's like a condensate surrounded by a thermal cloud. So this is the standard picture of we have sort of a superfluid and a normal fluid if we don't want to invoke condensation, but obviously in the trap here. And then what we've done is we've derived the full set of equations that would describe the condensate coupled to the particles. The particles are described by a Boltzmann equation, and then you have the condensate over here. And of course, both are also coupled through the gravity. The gravity couples the total sum of condensate plus particles, not just one or the other. So and you can have collisional properties between them and so on. Okay, so in fact, so this model we've derived unifies both of these dark matter models, both the lambda CDM that people have been using for decades and this fuzzy dark matter. They're both special cases of that. But we've gone one step further because we want to continue to consider stochastic processes and noise. So we have a full model that actually includes extra dissipative terms and the appropriate noise terms and so on. And what we have is now this model that we have derived is basically encompasses all of these models that I've discussed today. So if we ignore scale factors, expansion of the universe, we put atomic masses and so on, and we ignore all kind of noises, then we recover this standard Gross-Pitaevsky coupled to a Boltzmann equation, collisionally coupled as well. If we keep the noise terms, but treat the upper part of the system as heat path, basically, then we recover the stochastic Gross-Pitaevsky equation that I used to model this sort of non-equilibrium growth and equilibration process.
And if we actually go to different limits of those two, we recover the standard lambda CDM as a special case, and we also recover the fuzzy dark matter or Gross-Pitevsky-Poisson as another special case of this system. So with that, I've come to the end. So I hope I've given you a flavor, and I hope I've managed to connect these different contexts. I firstly discussed what happens in a harmonic trap, and I told you about the special role of a harmonic trap due to the specific way that this emitted sound or the wannabe emitted sound interacts with a soliton or a vortex in a trap, and how we can use that to control the motion. Of course, when you add thermal cloud, then basically there's dissipation. We can characterize these friction coefficients. I then told you how we can use these stochastic models in different dimensionalities and for different systems to discuss this crossing. So we discussed universal physics coming in the form of Kibble-Zurek for finite duration quenches, or phase ordering and self-similarity at late times in the process. And then I also gave you a flavor of how we can use these techniques we learned from quantum gases to perhaps say something meaningful about cosmology. And I'm not presenting that here, but we've gone further. We've done more things. We're now taking actual data from galaxies, these rotational curves that invalidate cold dark matter and suggest fuzzy dark matter is correct. And we can see that, in fact, you actually need non-zero interactions to be able to mimic these galactic rotational curves. So with that, I've come to the end. Obviously, I haven't done all that. In fact, I've done none of these simulations shown here, except some of the early stuff with the solitons and vortex. Okay, so the main real hero here is Gary Liu. You will have seen this actually in Andrew's talk on the neutron stars. So he was with me working on cold atoms, and he's the one who was driving these dark matter simulations, even though he's now working primarily on neutron stars. And then many of you know Paolo Comaron, who did the stuff on extern polariton, and some stuff in the core setting of ultra-cold quantum gases, and then various other collaborators. Thank you very much for your attention.
Thanks very much, Nick, for a talk covering a broad range of topics. I'll get in early with questions. You chose not to put net rotation into your simulations of fuzzy dark matter, which may be okay for certain sort of elliptic galaxies, but for most galaxies, spiral galaxies, bar galaxies, there's net rotation. Is that something you plan to?
Yeah, absolutely. I mean, basically, to be honest, and coming as a non-cosmologist, I mean, you have some kind of observations, and then you're trying to find how to model these. And these are trends, and it might be that this fuzzy dark matter trend goes away. I mean, there are people who are thinking about that, so rotation is one very important thing. Another thing that we don't have in here is coupling to baryonic matter. It's there, and it can't be ignored. We don't know. I mean, currently people say, well, this fuzzy dark matter probably doesn't couple to baryonic matter, so we don't need to worry about it, but this is just pulled out of a hat, right? So there's many ways to get the same thing. For me, what strikes me with this kind of thing is basically the questions asked. Is it, and people are very bitter. I mean, cold dark matter people will not hear anything about fuzzy dark matter. And fuzzy dark matter are convinced that cold dark matter is fundamentally flawed. But actually, it's Gross-Pitevsky versus Boltzmann. That's all it amounts to.
Any other questions?
Yes, so what we do is we take rotational galaxies which are believed to be dark matter dominated because we don't have any coupling to baryonic matter, and then we try to fit, we have some more upgraded Ansätze that we have actually created basically for for how to model the density. So it's not, these simple models don't quite work. We've come up with better models that will soon be on the archive. And then we use those better ways of understanding how the densities look like. And we vary the parameters so that we can actually match the rotational curves. And we have found that there is a unique combination of a single mass and a single interaction strength with some obviously, standard deviation that can actually mimic these things. So on the basis of what we've done, looking at a certain set of galaxies that are dark matter dominated, what we find is that it is incompatible with G being equal to 0, and we have a specific constraint on mass and interaction strength. So basically, if other galaxies don't fall on that same thing, that should already invalidate the fuzzy dark matter. And that's, our motivation is not to invalidate it, it's to test it. But basically, you need to probe different galaxy clusters and see if they all provide the same unique range of parameters.
We have one final question, Dan.
So thanks a lot, Nick. And sorry for not quoting your earlier work.
It's okay, it's so much stuff out there.
Thank you. It's really great work. I have just a curiosity on the last part.
Yes.
Your work on the cosmology.
Yes.
So I'm wondering whether you really need to make the hypothesis of having a superfluid to make the whole explanation, or the only thing that you need is a fluid with a given equation of state.
You need a quantum pressure, basically. Yeah, you need something to stabilize. So there is ordinary pressure, but that's not enough to stabilize the system.
But suppose there exists a new fluid that we don't know, which has the same equation of state as quantum pressure.
Yes.
Could you imagine an observable, a astrophysical observable, which would test the superfluid nature of the fuzzy dark matter?
I think that's one step too far of what people are thinking. At the moment, it's trying to see how it matches things. So basically, the only thing that goes in here is the quantum pressure. But what is remarkable is solving a Schrödinger equation actually captures the domains. So it seems that the Schrödinger equation, but as I said, it's effectively like a Boltzmann equation, is enough. So you need something that will give you similar features to that. But it will be very hard to probe this superfluid thing. At the moment, everything is so indirect. So this would be like a much later stage of worrying about the problem.
I see. So, if I understand correctly, what matters so far is the equation of state. So you need something which has the quantum pressure in the equation of state.
Yes, but you need to be able to reproduce also everything. So all these dynamics.
All the equation of states in the different regimes.
Yes, yes.
But I think to probe the superfluidity would be really great. Go for that.
Sorry for that question. That shows my incompetence, basically. I was wondering the way how you couple your gravitational field to your mass. This is just classical Newtonian physics, if I understand correctly.
Yes.
However, typically I'm informed by as a physicist that in galaxies there are supermassive black holes. Is that a problem somehow, or to leave this away, or?
So supposedly not. So at the typical speeds that people look at in galaxies and everything, and at this low mass, the system is actually very far from being in the relativistic limit. So it's okay. There is a whole class of other models. I believe these are called MOND, right? That actually include relativistic effects. So there's many different models of how people are trying to fix these. So I'm not going to say that it's not relevant. It is believed that basically classical Newtonian is enough to describe those, but I'm not going to put my hand on fire for that. That's what people who deal with these observations and look at the parameters and everything believe is the case, but there is no consensus. There are people who will say that this is fundamentally flawed. So, there's camps.
Thank you.
Thank you.